already. Yeah, it's 54. So now it's the next section of our course here, and what we will do is we'll talk about neural networks and deep learning here, right? But what we will do is deep learning, we'll spend some time, I don't think we'll get to it today, maybe tomorrow morning. What happens is there are some very specific use cases for it, particularly, for example, image processing, face recognition, and so on. And so we'll just cover it. So it's not really, for some IoT applications, yes, it may be applicable, but you know, the other simpler things is what I feel are more interesting. So we'll spend more on the fundamentals, which are the neural network part of it. I'll just give a brief overview of deep learning and something like that. All right. So let's start with where this whole field comes from, this deep learning thing. And it really comes from our desire as humans to develop computers that can mimic the human or an animal brain, right? Because so far, even today, the best processor or the best computing that we know is the human brain, right? And so if I have a computer, I want it to be the best, which is the human brain. So that's where I want to go, right? So that's where it started. So if you look at what a modern computer is, it's one of the most important technological things that we developed in the last century. And what happens in a modern computer is, you know, you process information, and it's a digital thing, so binary things and so on, binary operations. So a program is a list of instructions or operations that you want to do on data. So that's what your computer does. One by one. Serial computer. So then I'll ask us, how many operations can my computer do in 1 second? If you have a CPU speed of 2 gigahertz, in the best case, you would be doing 2 billion operations per second. That depends on my clock rate. So with a clock rate of 2 gigahertz, I'm doing 2 billion operations per second. But if it is not a parallel computer, right, if it's a serial computer like this is the key thing. At any given point in time, only one instruction is being executed in the CPU or in the processor. Right? It's serial, one by one, right? That's fine. So that's what computers do. On the other hand, as we will see, the human brain is a little bit different. It has less capabilities in some ways, but it cannot do 1 billion operations per second. So you get this slowly. But it does things in a different way, maybe in parallel, so it still gets good performance. Right? So we all hear about AI and so on. So the question is a computer more powerful than a human right now? The answer is yes and no. In some cases yes, some cases no. So for example, solving equations, right? I don't know how to solve this. Really, I mean, that's not true. I can probably solve it, but you know. It will take time for me, but a computer can solve it. And when we think about intelligence and other things, these are the examples you see. So chess is supposedly a very complicated game, right? And for a long time, that was the thing to do. Can a computer beat the best chess player in the world? And IBM's Deep Blue did that in '97, 20 years ago. And more recently, there is another game called Go, quite popular in Korea and China and so on. And this is, people say that this is much more complicated than chess because the number of possible moves that you can make at any point is much larger than in chess. So in chess, if you're trying to figure out what's the next move I want to make, so you look at your candidate moves. So there's a space. And usually computers, what they will do, and not just computers, people like Vishwanathan Anand or whoever these days is Carl Magnus, or whoever is the champion these days, they don't just look at one move. They think, okay, if I make this move, my opponent will make that move, then I'll make this move, and then, so they look at many moves in the future. But the number of moves grows exponentially then. And here it grows even more. And this year, there's a computer which beat this guy. There's a Korean guy who was the world champion that beat him. Right here. So computer seems to be winning, right? But then there are other cases in which a computer fails. So for example, why human? Let's consider pigeon. right? Like a bird, and small. We don't, well, I don't know. So, some cases we associate some intelligence with pigeons because they were supposedly letter carriers, right? I don't know. I'm too old, but yesterday, I just turned on the TV, there was this Salman Khan, Kabutar Ja Ja Ja. You guys are probably too young to remember those songs, but when I was in school, those were the songs maybe, or when I was in college. So anyway, so let's compare the intelligence of a kabutar, a pigeon with a computer, right? And there was this guy Chagall. He had an experiment. What he would do is he would try to not Chagall. There was this Skinner. He would reward birds if they did the right thing. So he was trying to train them. So he would show them two pictures by two artists. For example, one is Chagall, the other is Van Gogh. Show them the picture. And he was trying to teach them that, okay, pick the pictures by this guy. If they pick the right picture, give some whatever seeds or whatever fruit pigeons eat. So that's reinforcement. So every time you make a correct decision, you get a reward. And at some point, the bird can recognize. And then, to me, these things are very, I'm not an artistic person, so this is Chagall's painting, this is Van Gogh's painting. If I didn't do any better, I don't know who. Can I tell from a distinct style who did what? Maybe you can, some people can, but I can't. Right? But the bird, they showed the bird a number of these images. And every time the bird picked Van Gogh, give reward. So the bird knows how to pick Van Gogh. And so what was the accuracy? So in this case, what we are doing is, we are testing on the training data itself right now. So I trained the bird on a number of pictures, then I show a bird a picture. If it is a Van Gogh picture, the bird gets excited or nods its head in some direction, and then I say, okay, you have classified it correctly. So it turns out birds are doing 95%. And a computer, 100%, right? This is training data is equal to test data. Computer can memorize everything. Every picture you show, it's like our rote learning thing, right? Computer can easily do 100%. You can do, I can also probably do 100% of this. So this is not surprising, that's fine. But what happens if I give you a test data which you have not seen before, right? The pigeon can do 85% accuracy. So this is a Van Gogh which the pigeon hasn't seen before. Computers cannot get that close these days. Quite far away. So you can recognize something you have seen, but to me, I think it's the same guy sitting somewhere drawing something. So it's the same to me. But if you are very careful about brush strokes and something, you can tell that this is Van Gogh, this is Chagall. And birds can figure that out too, but computers can't so far. So there are still some places in which we are sort of winning. Right? So what is the pigeon doing really? It's not memorizing. It's not memorizing things anymore. It's looking at patterns and recognizing them. So what happens is when painters paint, they put their brush strokes in a certain way. Or they put their color, they choose their colors in a certain way. That's important rather than, there was yellow here and then whatever this color is. What is this color? Green or blue? Green. So there is green on this side. That's not what is important. Some other characteristics which are hidden sort of, that's what we want to know. And that distinguishes one artist from another artist. Yeah. And so somehow they learn from the training process and make predictions. So there's something different in our brains and the way the computers are doing things. Right? So let's look at what the brain looks like. So brain is basically a set of these cells, right? And it's called a neuron. And we want to get into the details, but there is a nucleus here. And there are these things called dendrites. And these dendrites, and this guy here, this is called an axon. And axon from one thing will connect to the dendrites of another cell. So it's like a network. This is the output cable. These are the input cables. The input ports, and this is the, and you don't necessarily have only one axon, or at the end of the axon you can have many of these So you will connect to many different. So one of these cells can give output to a number of other brain cells. And there are some words for it, where they connect, it's called a synapse and things like that. That's right. But the idea is that a brain will process certain things, and based on that, if it thinks that something is going on, it will get excited, and if it gets excited, it will send a signal to the other cells it's connected to. So how many how many cells or neurons do we have right now in our brain? About 100 billion, 10 to the 11th, right? And each one has 10 to the power of, and the total number of synapses or connections is 10 to the 15. So connection per neuron is somewhere of the order of 10 to the power of 4 or 5. So this guy has about 10,000 to 100 or 1 lakh, as we say, right? Of these things here, quite a lot, quite a lot. And the neuron switching time, the time it takes for a neuron to fire, that something has happened, is quite slow actually. You may think, oh, this is 1 millisecond, quite fast. But compare it to a computer. It can turn on or off in 1 nanosecond, right? If you're working on a gigahertz clock. So a computer is 1,000,000 times faster than this. But if you give me somebody's face that I know, I can recognize very, very quickly. Right? If I see Hari Gupta now, I will say, oh, this is Professor Hari Gupta. I can do it quickly. So what is happening is, it cannot be done sequentially. There is something else is going on. So what is going on is parallel computations. So all our neurons, it's not like one neuron, then another neuron, then another neuron. All neurons are working in parallel to figure out what's going on. So it's a very, very massively parallel architecture. Right? And before we get into neural networks, it's important to understand how neurons work. So let's spend a few minutes working on that. And the neurons will, they're basically electric signals that are being passed on through the axon to the next neuron and so on. Right? So there are different kinds of things that can happen in a neuron. You can excite it. So for example, my eyes, right? They're converting light into some signals. And they're sending these signals back to whatever the brain is. So that's exciting. And they're sending signals that I'm observing something. Also, sometimes we may inhibit it. If you let's say injure yourself, you take a painkiller, right? So what happens when we have pain? If I break my hand, signals will go from here to my head saying something is wrong. That's pain. I register it as pain. But if I take a morphine injection now, what will happen? It will inhibit those signals. So I will not feel the pain. So it's possible to do the reverse also. You can excite it, you can inhibit. Both are possible. Right? And some ways you can also control. How excited do you get? If you drink coffee, you get tea, that's supposed to excite us, right? It makes us alert. And so on. That can modulate what's going on too. Right? And if you excite the neuron sufficiently, then we say it fires. So what is exciting the neuron? It's getting some signals here. Other people are giving you signals. Maybe my eye is sending some signals to whatever is processing my vision. So I am getting signals from here. A lot of signals, 10,000 signals, 100,000 signals. I sort of add them up. And if it is high enough, I send the signal to the next guy. Right? So that's what's happening. So if the neuron becomes sufficiently excited, it will respond by sending an electric pulse to the other guy. And then these spikes travel down each branch and sub-branch of my thing. And the brain at some point figures out what's going on. Right? And this part here, which I said, you have to excite sufficiently. You don't always get an answer. Or your neuron doesn't always fire. And then, we don't really want to get into this. This is the more of a biological thing, why it excites. It's really the ions coming in and getting through my cell membrane. I don't care. Right? Something happens in the biological level. But, for example, if my excitations are too small, not much is happening. So I will not fire my neuron. But if I cross a certain threshold here, I fire. And the reason I'm telling you these things, well, it's important from the context of neural networks. Because ultimately we're trying to model how the brain works. Alright, so I'll try to hopefully bring all of this together when we're talking and so on. And there are other things that we have to worry about. Let's say I get a lot of signals. What happens? How does the neuron react to it in a biological system? A couple of things. It doesn't mean that, so if I get a lot of input, it doesn't mean I get a very high output. It's just a trigger. Lot of input. So let's go back here. If I reach this threshold, I will give this trigger. If my input is this much, still the same output. Okay? It's not that I'll give a very high voltage or whatever it is, not like that. It may be that I do it more quickly. I fire more often. But the amplitude of the fire is still the same. Okay? That's fine. And when it becomes excited, as you give more and more input to it, the rate of firing will increase, more output. Also, if you receive an inhibitory signal, then it will slow down. Sometimes it will become noise-like thing. So that's fine. And what does it do? The major job, and this is where what neural network will also try to do is, its job is to process it. It's receiving some information in the form of an electrical pulses. Every other neuron is giving it electrical pulses. That's what you're getting. And we will see that in our neural network also there is something analogous. Each neuron or perceptron in our neural network will also get input from others. Now, we have some kind of a complex dynamic sum of these inputs. So I'm getting inputs from so many other nerve cells. What I will do is, I will treat these signals in a different way. Not all the inputs will be treated equally. Some brain cells I'm connected to, I will say that these are more important, especially when I'm doing vision, let's say. If I'm doing speech, I'm trying to listen what other people are saying, I will give more weight to somebody else, some of the other cells. So how much importance I give to different cells, that sort of figures out what I'm doing and what I'm doing to the signal. Right? And these connections that I'm getting from the others are crucial for excitation. If, for example, I have a connection to another neuron and I inhibit it, I'm not going to excite myself. So if, for example, there is part of my brain which is responsible for vision, if it is getting a signal from some cells which are responsible for, let's say, smell, shouldn't react. Right? Vision and smell, let's say they're not related. So what I will do is, the signals I'm getting from the smell part, I will make them close to zero. Or I'll inhibit them, I will not react to them. But if I believe that these are coming from brain cells which are connected to my eye, I will give them high weightage. Okay? So I can control what I'm doing with different kinds of signals. Okay? And the learning, or what I do with the process, is controlled by adjusting how much weight I'm giving to the signals that are coming in. That's the crucial thing. All the brain cells don't have the same weight. Different brain cells have different weights that they bring to the inputs. And the way these weights have been decided, that sort of tells the brain what it has to do. That's the fundamental thing that we want to take home from here. So now let's come up with a model for a neuron. This is what the neuron was, right? So we had these input ports, and this was the output port, essentially. So if I want to model it like an engineer, what I say, okay, this is my neuron. It has a number of inputs coming in and one output going out. So now the question is, what's happening here? Am I adding these? Am I multiplying this? Am I doing some kind of a convolution? What am I doing here? Right? So that's the function that we want to come up with. And hopefully recreate the same function in a computer. So it can behave like a brain. That's what we want to do. Now, when I have to come up with a function, I have many choices for a function. And no matter what you're doing in life, research or whatever, it's always best to start with the simplest explanation or the simplest case first. So a simple thing might be just add them up. That's what it is doing. I believe what they're doing is they're just adding it up. No matter what input you're getting, you add them up. And that's my output. So the output is the sum of all them. That's the simplest case I can think of. But what that turns out is, if you use this particular model, so the idea is this, even with your research or whatever, you start with a simple model and try to see where it breaks down, where it doesn't work. And when it doesn't work, you try to address that problem, fix it. But when you fix it, again go with a simple solution. If that doesn't, you don't come up with a very complex solution in the first place. Start simple. So, let's say this is my simplest one. We add everything at the input. But if I do this, if there's a lot of excitation coming in, it says my output can be as large as possible. There's no limit to the output. But we just saw previously that that's not the case. There's a limit to the peak here. And my brain is not going to create a 500 volt signal, for example, or 3 ampere signal. That's not going to happen. So what I want, this doesn't work. This is very simple, but doesn't work because there is a upper bound. There should be an upper limit to it, or maybe even a lower limit to it. So let's put those limits in. And one option is to say, whatever input you're getting, I will pass it through a function that will limit the output range. Your output range will not be infinite. It will be limited. And general name for that is what is called a squash function. So you're squashing your thing and making it within a certain range. There are many, many different squash functions possible. As an example, this one, simple threshold. As soon as you reach a particular threshold, you will fire. In this case, the threshold is set to 0. As soon as you get some excitation, or your sum of your excitations is positive, because we're talking inhibitions also, right? I can give you a drug which will slow down, or give the opposite signal. So as soon as your sum becomes positive, you fire. But you don't have to fire at 0. You can set the threshold. You fire at some 1 or 2 or 3. And that's what this is. If you don't want it to fire at 0, you want it to fire at some particular threshold, either positive or negative, pick your B appropriately. This is not the only squash function. See, this is bounded between 0 and 1, or any two limits you want. This is another possible value. This is very sharp and discontinuous at the origin, and this is not continuous here. Let's say you want a smoother function. You can go for this piecewise linear function. This is much smoother than this. This is also a squash function. If you're less than some value, you're 0. Between 0.5 and negative 0.5, you sort of increase linearly. And beyond that, you stay at 1. That's another possibility. And then later on, we will see which one we want to use and so on. And then, given that these squash functions are there, now this becomes my mathematical model for a neuron. These are the inputs coming into my neuron. These guys. These inputs that are coming into the neuron. Those are my xi. So xi is the input coming from previous neuron 1, previous neuron 2, and so on. And what I do is, I assign some weight to each one of them. This says how important I think that particular neuron's output is for me, for whatever job I'm trying to do. If it is not important, I'll give it close to 0 or even negative. If I think it's very important, weight will be higher. Plus, so I'm adding them up, and you see that I allowed for a threshold value here, or a bias value, if I didn't want it to fire at 0, or if I want this thing to move to this side or to this side. So that's this bias value, B of k, and I'm adding it here. And what I'm getting is the output. So I add all of this up, all the inputs. Any input value multiplied by the weight. Xk, x1, wk1, something. So I add all the weighted values of the input and the threshold value and pass it through a squashing function. That's the output of my neuron. Okay, simple enough. So assign weights to all the inputs based on what you think is important, add them up, put in the bias value, pass this through a squashing function. That's my output. And this is the effect of the bias that I was saying. You can move your boundary or you can shift, right? That's fine. The other way, or a more compact way of representing this, that's what we do. Here I have this sum of all the input values plus the bias. Instead of writing two variables here, I want to write only one variable. I want a more compact representation. So what I do is, I represent this bias also as an input variable. Just to make life easy. Mathematically, no difference. So this bias will also be an input value with where x0, let's say. And that value will always be 1. And the weight will be the bias value. So I can do it that way. And that's what I'm doing here. UK plus, so the sum of all the inputs and the bias, I just represent, instead of going from 1 to m, I go from 0 to m now. And the 0th one is the bias, where the input is always 1 and the weight is equal to the bias value. Essentially it's the same thing. But instead of writing two different ones, I just write it as one, so it makes life easier. So this is what it will look like now. The previous diagram here, this thing has moved to the input side. So here I have. Okay. So now again, bias is one of the inputs that I consider, but the input is always 1. Right? And so now at the output of this, I have the sum, weighted sum of all the inputs, and then I pass it through this quotient function. Okay. Question so far? What is it? 10:25. We have 1 hour 5 minutes. All right. Okay. So now let's see what squashing function should I be using. Let's go for. So we looked at the hard limiter thing, and then we also looked at the piecewise linear thing, right? So what is good and what is bad? So if you look at this guy, and before independence, in those days, this guy came up with this model for a neuron. It's not really a new thing; it's its own thing. And this is a very, very hard threshold function, a hard limiter. So the problem with this, using this in many of our cases, is the problem is that this is not continuous. Right? And ideally, I would like a continuous function. And it also doesn't distinguish between input levels. This is also a 1, this is also a 1, this is also a 1. It doesn't distinguish. Sometimes I want to have some distinguishing factor. I don't want to have a range of infinity, but at least something, that this input was higher than this input. Right? I want something of that. So this is fine, but not very useful. So let's try this guy. It does distinguish between input levels, right? If the input level is here, I will get maybe something. If the input level is 0, I will get 0.5. If the input level is here, I will get 0.75. So you can distinguish that. But the problem is, this is not differentiable. So at these points, here and here, it's not differentiable. So that's one problem. So what we do then is, we use something called a sigmoid function or a S-shaped function. Looks something like this. And this is the expression, general expression for this. 1 over 1 plus e to the power of negative AV. If you give any input V, this is what it will be. And this A is the slope parameter. It says how quickly you rise and how slowly you rise. That controls it. What it will be, as you see asymptotically, as V becomes small, this will go to 0. Right? And as V becomes large, this will go to 1. Right? And the good thing about this function is, this is limited, but it's differentiable everywhere. And that will be useful for us later on, as we will see. So in many cases, we will use, in most, not in many, in almost all cases, we will use something like this for our neuron model. And if you look at the derivative of this, and we will use this later on, if you look at what is the derivative of this, we can take the, you can do chain rule and whatever. And in the end, what you will see, the derivative of this is a times the function itself and 1 minus the function. Right, so derivative of this function is a, the slope parameter, 1 minus the function. Believe me, if you like doing calculus, go and do it. Right, so that was sort of how the brain works, right? And any questions so far?
Which kind of signal for the neurons may have it AC signal or DC signal, or might be both kinds of signals?
Okay, so the question is what kind, right? To be honest, I think this is DC. It's like it's usually just a pulse. It's not DC in that sense, it's a pulse which you get. You get a trigger. You get a pulse and then that registers as something.
But a negative pulse also?
You can have a negative pulse. And the height of the pulse can be small. Or by using the weight in the connection between the two neurons, the height of the pulse can be controlled.
But in figures we have seen that it's a kind of some signals vary.
Yeah. So the thing is, when you do a pulse in real life, you don't do a pulse like this. Very difficult. Maybe something like this or something like this. It slowly goes up. Slowly means,
Yeah, very
it goes up and then comes down. Right. So now let's come to, hopefully we have understood a little bit about how the brain works. And now let's try to create an artificial machine that will be similar to what the brain does. If you want to learn more about this, this is a reasonably decent book by Simon Haykin, Neural Networks and Learning Machines. If you want to get into this. If you're noting down, I'll just give you a second to write it down. Okay? Alright. Okay. So let's look at what's a neural network. Let's try to define what a neural network. A neural network is a massively distributed processor, parallel processor. The examples we will do in class or we will see in textbooks are not, they are parallel but not massive. There's 2 or 3 or 4 neurons because we can't handle anything more than in our brain. But when you're trying to implement it, as long as you have the computational capability, you can have as many as you want. And that's not a problem. And what we have is these neurons are very simple on their own. Each neuron just does this, like we saw before. You get a sequence of you get a number of inputs, add them up, pass it through a triggering thing, pass it through a squashing function. So simple. It's not doing anything fancy. But the way we will connect them together will hopefully make a difference. And it will be capable of recognizing its structure, which means how are we connected, what are the weights we are giving to each of the inputs. That's my structure, it will be able to do that. And the knowledge that we have, the learning process, will be based on some training data. We have to do that. So the weights and the structure that we will need will be based on some kind of an input data. And the knowledge is learned. You give me the input data, which says, okay, if you have this, then the output is this. Right? If this is the input, then this is the output. How do I know what's the concept behind it? In this case, all the concepts are in terms of the weights that I assign to other neurons. The concepts are essentially weights. And how do I know those weights? Somehow we have to learn them by adjusting, by trial and error maybe, things like that. And we'll look at specific algorithms for learning the weights. Right? So just as a quick thing of strengths and what are the benefits. So the thing is, it's quite general. You can give it sort of any problem and then it will give you an output. It generalizes quite well. And it's massively parallel, so it can do many, many things. And it can handle non-linearity. Most things in life are non-linear. Output is not linearly proportional to the input. So it can handle non-linearity. And a very simple way of visualizing is this. If you give a little bit of input here, you will get an output. But at some point, it will become non-linear, right? So this is a non-linear function you see here. So it can handle non-linearity. And it's quite adaptive. You just change some of the weights and you're doing something completely different. You get a new set of training data, just change the weights, not very difficult, and you have something new. And it has fault tolerance built into it, because you're getting input from a number of different neurons. In the case of the brain, 10 to the power of 4 or 10 to the power of 5 neurons. If one or two of those neurons is giving you wrong information, hopefully it will not matter much, because it's 1 of 10,000. Right? So it's more tolerant to noise and so on, or faults. And these are the properties. So you have many neuron-like threshold switching units, and these units will be interconnected, and they will be weighted. And the emphasis really here is on how to figure out the weights, because the weights are the hypothesis. If you pick one weight for the whole set of neurons, you have one hypothesis, pick something else different. So let's take an example of what different kinds of. So this is the most general sort of thing. Is it the most general? This is probably not. This is one of the architectures that you will see quite often for a neural network. So we will start with a set of neurons that we will see at the inputs. The inputs have only one incoming thing rather than 10,000. So inputs are one. And then in the middle, we'll have one or more layers of other neurons. Most of the time what you will see is each input goes to every one of those neurons. This is connected to this and this. This is connected to this and this. In the general case. If you don't want a connection, put the weight to 0. That's fine. But in general, just to make life easy, we will connect to everybody. And then the things in the middle, they can also connect to the next layer. And finally, you have your output. And each output will be each output only one thing. Or if you're classifying a multivariate thing, it will have two numbers there, maybe 3 or 4. Now these are the ones that are directly accessible. You can control the input that you're giving based on your sensors or whatever it is, and you can see the output or the result of this. These you don't see directly. So these are hidden layers. We call them hidden layers. And another thing is, in general, you just don't have to connect to the next layer. You could possibly connect to the second layer or the third layer or the fourth layer. But usually we wouldn't do it. Makes life more complicated. It is also possible that layer number 2 feeds back to layer number 1. In human brain that sort of happens. But here there are ways in which we can accommodate it. But more complicated, we don't want to get into that. So this is a single layer architecture. We have inputs that are directly connected to outputs. There are no hidden layers here. And this is a more general case where we have a sequence of inputs, sequence of outputs, and the hidden layer. And these, what they do is, they will look at the inputs, do some computation, give it to the output will do some computation, and then go forward. And then the question is, how many of these do I want? Do I want 1? Do I want 2? Do I want 3? 4, or so on? So what each of this is doing, right? If you go back to our simple case like this, here. What a neuron is doing is, you are getting the data, you're getting your inputs, and you're giving a single output. So essentially, if you think about it in just 2-dimensional space, visualizing higher dimensions is similar, but in 2 dimensions, what it is doing is, you're giving me all these inputs. So these X's and O's. Maybe there are 2 classes, just imagine like that. What this is doing is, this is W1, X1 plus W2, X2. should be greater than 0 here, right? So it's sort of like an equation for a line. So essentially you're trying to come up with something like this. So you're trying to learn the weights which will control this line. Should this line be like this, or should this line be like this or the other? And that's what essentially we're trying to do. If you just have one neuron, or one in the hidden layer, you just have one line. If you add another one, you can have 2 lines. If you add a third one, you can have 3 lines. In this case, one line is good enough. I can separate them. This is what is called a linearly separable case. I'm lucky here. In most cases, it will not be linearly separable. So, as an example, your test cases might be like this. So, we have 2 classes here, the stars and the pluses. And you see here, I cannot draw a single line anywhere that will separate both of them without any errors. I cannot do that. So if I have just one neuron and I train it, maybe I'll come up with a line like this. If I have 2 neurons in my hidden layer, so there are two neurons now. So the first one maybe will give this, and hopefully the second one gives something like this. So this point, for example, the star point. So let's say the decision here is what? If you're on, so you're watching like this, oops. So you're watching like this, so this is what? Left, right? So if a point is on the left of the line, it's a star. If a point is on the right of the line, it's a plus. So here, this will be classified as a plus. This will be classified as a star. If I have 2 lines, now I have 2 classifications for each point. This particular point is classified as a star by this line as well as this line. So I'm fairly confident that this is a star. This one will say that this is a star, one will say that this is a plus. Which one should I believe? Many possibilities. One thing is, if it is closer to this line, take it as a star. If it is closer to that line, take it as a plus, whatever it is. Okay. If you have 3 lines, now you have this. If you have 4 lines, you can do this. If you have 5, 6, 7, 8, and so on. But as you see, as I'm adding more and more lines, so I'm adding more and more neurons, what is happening is, hopefully I'm coming up with areas where only one kind of point is present. Right? In this region, only stars are present, only stars, only pluses, only pluses, only pluses, and so on. Right? So hopefully, by adding more and more neurons, I can come up with this. So this is the whole central idea about what we are trying to do. The reason for adding more neurons and so on is this. And at the output layer, what will you get? For example, here, let me go back here where it's easier to visualize. At the output layer, this is the output. It is getting a classification from this guy, and from this line, and from this line, and from this line. So for the 4 case, this is a 4 neuron case, right, previously. So for every point, it will get a classification from this line, it will get a classification from this line, it will get a classification from this line. Now this has to make a decision. Is it a plus or a star? How will it decide? Based on the weights it has given to all of these lines. So I'm getting 4 classifications, but I don't treat them equally. I give them weights. Right? So the weight will decide what I'm finally accepting it as. And we will learn how to assign those weights correctly or smartly, rather. And then this was the feedback I was talking about, and now a layer can feed back to a layer before it, but more complicated, we don't want to get into that. So when should we be thinking about neural networks? Right? So we have learned decision trees, and this is neural networks, and hopefully tomorrow we'll learn something else. When should I be thinking about neural networks? Usually when your input is very, very high dimensional. Could be real, could be discrete, doesn't matter. Because with high dimensional data, sometimes graphical models and other models becomes a bit difficult. This one is fine. And we don't care about the output. Could be discrete, could be real valued, could be a vector of values, doesn't matter. And it handles noisy data quite well, and we saw why, because you have a number of inputs. Even if one input is noisy, it's okay probably. It will get absorbed by the correct values from the other inputs. And in this case, usually the amount of time it takes to figure out the weights can be long. If you're willing to have that, fine. Right? And the thing is, once you have the weights, now you give a net test data, that's quick. Testing is quick. It's the training which takes long. Okay? And it's very good if you don't know the range, the target function, what it looks like. So when we were doing candidate elimination, we said it's conjunction. Sometimes I don't know. For example, when I say classify this image as a boy or a girl, what should I be looking at? And is it conjunction, disjunction? I don't know. So it's good in those cases. And the human readability of this is very interesting. I don't care, if you don't care what's really happening inside the neural network, in the weights and what's happening at each of the hidden nodes, you don't care, all you care about is classification, which is probably what most of us worry about. Maybe as engineers and scientists, we may worry more about what's happening inside, but if you ask somebody who's using these applications, they don't care. I don't care what's inside. I don't care how the doctor figures out why I'm sick. I care, I go to the doctor tells me take this medicine. Why, how, I don't care. Right? I go on a plane, I don't care how the pilot is flying it. As long as you take me to the destination, I'm okay. Right? That's what this says. Common applications are speech and image recognition, image classification, financial prediction, and so on and so forth. So now let's come up with a practical situation and then try to build from here how we go with neural networks to solve engineering problems. Right? So we hear all about these self-driving cars and so on. These just probably coming in. So in Singapore, we expect our first real driverless bus to start in 3 years or 4 years or something like that. Right? Maybe a bit difficult here, given the way we drive in India or walk on the roads. But I think it will get there at some point. That's fine. So this is not new, right? This is 1993. You see, there's a laptop here, and this is a self-driving car. And this car, this learned how to drive on its own. This is in the US, near Philadelphia. Yeah, this is Pittsburgh, yeah. This is Pittsburgh, and they're driving somewhere close to it. And what happened is, there's a camera here. This is the camera. This camera is taking pictures of the road. Right? And it's feeding that picture an image. It's taking a picture, I think, a few times a second, maybe 10 or 15 times a second, not very much. And it's giving to the computer. And the computer figures out what should we do with the steering. Should we go left or right or something like that. And that's what it's trying to do. And the picture that we are taking, now we take pictures of whatever, 5 megapixels or 20 megapixels or something, right? This is just 30 by 32 frame. This is a 900 something, what is it? 960. Yeah? 960 not mega, 960 pixels. That's all. Right? That's good enough. Can drive about 70 miles. 70 miles is more than 100 kilometers per hour. Right? And quite long distance, 900 miles, 150 kilometers roughly, let's say. Right? Quite long distance. And how was it trained? 5 minutes of training data. There was a human driving the car. So what the camera is also capturing the picture at the same time. So what the neural network is getting is, when the road looked like this, the driver turned left. When the picture was like this, the driver didn't change anything. When the picture was this, he turned this way or whatever. maybe sharply like this, or maybe just a little bit, whatever it was, for 5 minutes. And then it can do all of these things. Right? So how is it done then? So let's look at the network here. So what we have is, we have a picture like this. Right? This is what my camera is capturing from my windscreen. And this is 30 by 32 pixels. So I don't know which is, so let's say rows. So we have 32 rows and 30 or whatever, 30 rows and 32 columns or 30 columns, it doesn't matter. What we are doing is, each one of them pixels is an input. So my xi goes from 1 to 960. So each one of these 960 inputs, so I'm just showing the top ones here. There are inputs here, 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 and so on. They are also connected. Right? And I just have 4 hidden layers in this case. Not very big. So each of these 4 hidden layers is getting inputs from all the 960 inputs. And then at the output, these guys had 20 output units. Why 30 output units? Why? Because, you know, when you're driving, the decision is not just straight, left, right. It could be a little bit more, right? So you need a granularity. And in their case, they said it's fine. So we have straight, all the way to sharp left, all the way to sharp right, and in middle. Little bit right, little bit more, and so on. So we have all this. So whichever output fires, or whichever output gives you the highest value, you probably take that and say, okay, this is my driving decision right now. And that's what you're doing. And this is what it looks like. So of what this matrix shows is this. I have these 4 hidden layers, right? Each hidden layer has 960 inputs. Let's pick one of those hidden layers. I don't know which one they picked from the book, but one of those. So what this shows is the weight it gave to each one of those inputs. If it is black, it gave a negative weight. So for example, to the pixel on the corner here, it gave a negative weight. How negative was it? Depends on the size. So for example, this one was negative, but a small negative value. This one was negative, but a large negative value. This one was positive, but a small positive, and so on. So we have, for that particular hidden layer, we have 960 inputs. And this hidden layer again is connected to 20 output values, 30 output values. So there is a weight assigned to each one of those 30 things. And that's what it shows. And if you imagine, like, so it's very difficult to, in general, say what's going on in the neural network, why the weights are like this. But if you think about this, it's a little bit, you can probably imagine what's going on. You're trying to drive. And when you're driving, you're trying to say, I'm going to go this way, I'm going to go this way. So here, if you see, a lot of weight is coming on this side, on the left side. So essentially what this is trying to do is, it's trying to figure out, should I be driving left or not? Should I be turning on the left side or not? And even in the picture you see, on the left side of the camera's image, I'm giving high weights. And on the right side, it's kind of darker, right? So if you want to imagine what's going on, it's basically trying to say, is it time to turn left? So the left side is being emphasized here. So what we now have is, we have a large matrix. You may say 930 by 32 is not large, but it's large. For me it's large. And from each of these, we have a black box of these many inputs into one of the hidden things. And I told you what these black and dark and things like that. So that was an introduction to how we would construct a neural network. But the main thing then is, how do we figure out the weights? Right? How do we figure out the weights? And let's spend the next 40 minutes or so talking about those weights, how we figure them out. So this is what, so the hidden layer, right, or any of those things inside, this is what it looks like. That's sort of my neuron. And my neuron model was this. I have weights that I give to the inputs. I have a bias. I add them up. I pass it through a squashing function. In this case, the squashing function is just a hard limiter. More than 0, 1, less than 0, 0. Right? Or negative 1, whatever it is. Right. And then we also, I showed you the simpler notation where, one way of saying this is the output will be 1 if it is greater than 0. Or I can write this W1 x1 plus W2, W0 x1. x1 is always 1, so x1 is not, sorry. x0 is always 1. So I don't have it here. So x0, W0, x1, W1, xn, Wn, that should be. Or I can just write it in vector form. W times x, the dot product, should be greater than 0. Same thing. Alright, fine. Now, this is what the decision surface looks like I was drawing here. If you give me a single perceptron, and I give you the weights in 2 dimensions, it will sort of come up with a line like this. Now, I'm trying to go towards how we figure out the weights, right? How we figure out the weights. So let's say my input function is like this. I cannot come up with a single line that will classify each and everything, right? But we'll come to that later. So that's what is called a, so in this case, this is the decision boundary. This is linearly separable. A single straight line is separating everything. In this case, I cannot draw a single straight line that will separate. So this is non-linear, right? And we will see how non-linear decision surfaces can be taken into account. All right. So now let's try to understand how we can put in the weights. Right? How we put in the weights. And let's say what I want to classify, I want to build a neural network that will do some Boolean function for me. Let's say I want to do AND. In the AND case, this is my truth table. Let's say 0, 0, 0, 1, 1, 0, 1, 1. And this should be 0, this should be 0, this should be 0, this should be 1. Right. And let's say when I say 0, or true false, let's say maybe I should go by true false. False, 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 true, false, true, false, false, should be true. And let's say I say true is 1 and false is -1. That's my xi values. So I have my xi's are either plus 1 or minus 1. So what will I have? So let's say this is x1, this is x2. These are my points. Let's say this is 1, 1, 1, 1. So I have a point here. This is true, true. Right? 1, 1. This is false, false. And I have 1 here and 1 here. I'm not sure. So x1. So this is true, false, false, true. But the way I should be classifying is, if these are circles, this is a star, let's say, right? So I want to find out a perceptron or a neural network that will do this for me. So essentially I want to come up with a line like this, right? So this will solve my problem. This will solve my problem. This will also solve my problem. So how do I classify this? So in this case, I can do it by hand itself. I don't have to do too much. What can I do? I say, all right, let's say, what happens when x1 is 1, x2 is also 1. What do I want in my function? This should be greater than 0 now. Right? W0 plus W1 x1 plus W2 x2 should be greater than 0. So W0 plus W1 x1. This is my equation, that's what I want. Let's make life easy. Let's say my weights are 0.5 here. Let's say I start with weights of 0.5. And this is also 1, this is also 1. So this plus this is 1, right? 0.5 plus 0.5 is 1. So this is greater than 0. So as long as this is greater than -1, I'm okay. Right? As long as W0 is greater than -1, I'm okay. So let's pick something for W0, which is greater than -1. Maybe I'll pick -0.8. So now let's try another one. So let's say what happens when this is -1 and this is 1. So this becomes -0.5, this becomes +0.5, so it's 0. So this is -0.8. It's less than 0. So my output will be false or a 0. So I'm okay. Same thing, if this is 1, this is -1, the same answer. So the only other thing is this is -1. So in this case, this is -0.5, -0.5, add them up, -1, -0.8, so -1.8, that's still less than 0, so I'm okay. So now I have built up a neural network that can do AND for me. This was very easy, right? I could do it by hand. And I can do OR and so on, but it turns out that I cannot do XOR. Right? Because in XOR, I will have 2 zeros here and 2 crosses on there. So I cannot have a single line that will do everything, right? So in XOR, where is it? Ah, that was okay. False, false, true, true. Right, and that's my pictorial representation. Cannot. So in that case, maybe I have to do something more fancy. So one single perceptron is not enough in that case. So for that, I need 2 layers or 2 levels of perceptrons. Then I can show that I can do it. And in general, why can I do it? Because any Boolean function can be represented as a function of ANDs and NORs and so on. No, ORs and so on. Right? So I can do it. And this is another way of doing, showing whatever I was doing. This is an AND I implemented. I can do an OR, but for an XOR, I will need 2 lines. So now what we are doing is we are interested in learning the networks of many interconnected. Not a toy problem like this. I can do it by hand, but in general I cannot. So what we will do is we will begin by understanding how to do the weights of a single neuron, which is called a perceptron. And the training problem in this case is we want to have a weight vector. I want to figure out the W's essentially. That's my training problem. You give me an input value, tell me what output values are. My job is to figure out the W's. That's my training problem. And there are 2 main algorithms for doing this. One is called the perceptron rule, and the other is called the delta rule or the gradient descent rule. Both are same. So let's start with the perceptron rule. In the perceptron rule, we will begin with some random weights. I will start with random weights. Okay? And then I will take one example, means training example. Right? I started with random weights that I wanted to put. I put the random weights, and now take every training example one at a time. Pick the first training example. See if we can classify it correctly or not. If we cannot, I have to modify the weights. Okay? And then we keep repeating. And once we have exhausted all the training samples, we can come back to the first training sample again and do our process again and again. And this is done. So this is a very high level picture of what I'm trying to do. And let's look at exactly what I'm doing. What does it mean to modify? How do I modify? So this is the algorithm. At every step, right? Let's say I'm now dealing with input xi. This is my ith training sample. I will wait. So this is my vector of weights, let's say. Right? I will change it. How? I will take the previous value of my weight and add some delta weight to it. The main thing is, what is this delta weight? And the delta weight is categorized like this. Now when I give this xi as input, right? So this is what is happening. So this is a single neuron right now. Okay. So we are not going into multi-layers yet, we'll come to that later. So this is what we have. These are my x1, x2, and then so on. And this is my output. So when I give xi, which is really a vector, I have given the inputs here, and I see what is the output here. But when you gave me this ith input, you also told me what the output looks like. You also gave me the label for the output. Now I go and check. Sorry. What is the target value? T. You gave me the input. You also told me what is the output. Output is the target. Target is T. And this is what I am generating. How different is it from the target? That's this. T minus O. So I see how different I am from the target value. And then I multiply it by the input. So I'm going to change my weights by this value. But then this could be large or small, and I don't want to make very, very large changes. So what I do is, I have a learning rate. I know that you are not close enough, but how much of this should I take back? If I just change like this, my weights will change very, very high values. I don't want that. So I have an era value, and this is the learning rate. So the problem is simple then. You figure out, you pass your input through your neuron, look at the output, see how you're different from the real value, and then multiply it by the learning factor, learning rate, and then that's it. Very simple. What we can show is, and we will not show it, but we will assume that we can show it, if the training data is linearly separable, and we're talking, and if you keep your error small enough, it will converge. If you try to do this on my XOR function, it will never converge. One time it will put some weight, next input you give, so I deleted my truth table. It was like this, right? 0, 0 was 0, 0, 1 was 1, 1, 0 was 1, 1, 1 was 0. I will train on this, I will get some weight. Next time I go here, I will get a different weight. And I will never converge on that case. And that's what will happen here. As long as it's not linearly separate, as long as it's linearly separable and so on, it's fine. So what is the intuition for doing all this, right? Why am I doing, what is the magic behind this? So what's the intuition? The intuition is, if your classification is correct, that means target is the same as the output. The difference will be 0. No need to update, this is 0. So that's easy enough to see that. If you have the correct answer, this will not make any changes to you, so that's fine. What happens if there is an error? That's the main question, right? So let's say your perceptron says it's a -1, and you made a mistake, the output is a +1. So what should you do? Why am I saying -1? This is less than 0. This whole thing has summed up to less than 0. So this whole thing should sum more than 0. Then I will get a +1, the real classification. Now to get the real classification, I cannot change the input. Xi's are constant. Whatever is the input is the input. I cannot change it. What should I do? I should make the W's larger. If I make the W's larger, this whole thing will become larger. So that's what I should be doing. And the weights must be in ordered, so you increase it. So for example, if Xi is 0, right, then increasing Wi will bring you closer. And if Xi is negative, you should make your Wi's smaller. And that's the idea. And this will happen, and it's very easy to verify. So for example, if your Xi is 0.8 and Eta is 0.1, and this is what happened, you give the opposite one, you figure it out, you get a positive increase. So when Xi is positive, this will also be positive. If Xi was negative, this will come out to be negative. So that works out. Now, what this works is, so we saw that this will be fine, but we need this linearly separable assumption and so on. So what else can I do if things are not like this? If it's not linearly separable, what's the other option? And that's this gradient descent rule, or the delta rule. And in order to understand that, what we had previously was we had a squashing function. Right? We had a squashing function. So if you assume a squashing function, then your input, no matter what input you get, if it's a hard limiter, it will be between 0 and always 0 or 1, sorry, negative 1 or 1 or 0, 1, whatever you want to say, or it will be within a limit. Let me remove that restriction. Instead of having a squash function limited unit, unit means that neuron, this is a unit. Okay? It's not unit like meters or seconds or not that kind of, this is a unit. Instead of having a squashing limited unit, let me have a linear unit. In the linear unit, my output is not limited between values, but it's just a linear function of the inputs. So, it could go as high or as low as you want. Fine. So now what I want to do is, if this is the function I'm using here in the neuron, I want to find the weights so that my output will be as close as possible to the target value. So in order to do that, what I will do is I will define an error function. So the error is the difference between what I really wanted to see, which is T, and what I got, which is O. Okay? And this is my definition. I will take the difference between the target and the output that I actually got. I will square it. And I'm going to do it for every one of us. Somebody touched some knob somewhere. Or maybe I did something. Yeah, this one went off. Alright, my fault. Sorry. It's going off again. I think the battery could run again. Okay, what was I saying? Yeah, so now we will do a linear unit, and my output will be a linear function. So I'm not limiting, I'm not squashing it anymore, right? And what I want is I want to learn the weights so that this will be small. The difference between the target and the output will be as small as possible. So this is what I define. It's a square of something. And this is for one particular input example. What I will do is, I will do it for all the training samples that you've given me. For sample number 1, sample number 2, sample number 3. So if it was a truth table, I have 4 input samples. Okay. So for each of my input samples, what I will then do is, I will add it up. And this is my error function. And what I want to do is, and if you look at this, I have put it as a function of my weights. Why? Because these weights determine what the output is. The output is essentially a function of the weights. So I want to find the weight vector that will minimize this. That's what I'm going to do. So let's see. in general, what we can show is in general, what I can show is, if your weight function is like this, the square of something, what it will become, for example, in 2 dimensions, if you're just dealing with x1 and x2, you have a parabola. You have a parabola, and this is a bit difficult to say, but this is one corner, that's another corner, this is a corner, and it's like this. The shape is a parabola with a unique global minimum somewhere. And if I have picked my, so these 2 vectors are my weights, well, it should have been here. Right? These are my 2 weights. If I pick the weight here, this is my error. If I pick the weight somewhere here, my error will be minimum. So what I'm doing is, I will start somewhere randomly. Maybe I start here. This is my randomly picked W1 and W2. Or W0. I will start here. But I want my weights to come here. So I'm going to do some kind of a search. And the way I will search is, I have to go towards here, right? So instead of climbing a hill, I'm descending in a hill or in a valley. So I'm going to look for what is the best way or quickest way to get there. What is the quickest way to go down? Find the steepest way to go down. If the slope is not too high, maybe I'm going in this direction, right? I want to go exactly down. And how do I figure that out? When I'm here, this is my surface. I take the derivative with respect to this guy. That will tell me, if I go in this direction, what will be my slope? If I take the derivative with this one, it tells me, if I move in this direction, along this axis, what will be my slope? And the vector, these you consider as what is it called? So I have, so the vector will be the sum of these 2 essentially, right? A vector sum, and that will tell me this is the direction to go in. And that's the idea. I will sit here, I will find out the gradient. I will find out the vector in which I want to go. And that's it. So the direction of the steepest descent along the, was there a question? So the direction of the steepest descent along is essentially the derivative of this error function with respect to each component of my W vector. And that is, in your calculus, we call it a gradient. Right? So I take the error vector and I take the partial derivative with respect to every of my weights. And then I will move in that direction. And moving in direction means what? What happens when I move in this direction? Essentially, I have changed my weights. Right? I have changed my weights, and that's what it is. So I calculate the gradient, and the gradient will tell where I need to go. So that's what I'm going to do. I calculate the gradient, and instead of updating my weights previously as I did like this, I will update it based on which direction I'm moving in that parabola that I had. And this is what I had. So whatever weight I had, I update it based on a delta weight. This delta of the weight, I'm sorry, this got cut, is based on the gradient that I just calculated. And as before, I just don't jump as much as I want. I have a factor here in front, which controls what's the sensitivity to it. And that's the whole algorithm. And then the next question is, what is this derivative? What is this derivative? Is there a nice form to it? And that sort of translates back to what kind of function that I want to begin with. The squashing function that I was talking about, the derivative calculation, I want something which has a derivative, which is differentiable. So if you look at this, right, this was my error function. If I take the derivative with respect to any particular weight, you can keep going around, and this is what it will come out in the end. And if you see, why did I have this half? Where did this half come from? If you could have asked the question, why did you have this half here? Just to make life easy later on, because it will cancel out. There is no reason for having, God didn't come and tell me have a half there, right? I just put it here to make my life easy. So that's what I have. So when you take the derivative, you can work through this math, and this is what it will come out to be. And if you take the derivative, this is what it turns out. It's the difference between what you wanted and what your output is, multiplied with the input value. This is very, very similar to what we had when we were doing the perceptron. Where did it go? Here. So this one was easy to understand. Why do I have this t minus o? Because that's the difference, that's the error I'm making. And this xi, in the previous case, this was sort of arbitrary. Looked like, why did you put the xi there? Why don't you just change by the difference of the error you are making? Right? The answer is the xi really comes sort of from this kind of equation. You're trying to move in the direction of the gradient. So this is my formal gradient descent algorithm, which says you can initialize to some random number your weights.
That will be negative also.
It could be negative also. It doesn't matter. Right? But we would want it to be small, close to 0. And later on, assuming that's not happening today, later on we will see that why we want it closer to 0. The reason we want it close to 0 is if you look at your squashing function, the sigmoid function, looks something like this, right? Like this. Very, very non-linear here and here. But around the origin, it's more or less linear. So we want to start off with the linear region and then hopefully go to the non-linear regions. And I'll talk about that, why we want that later. Okay? So essentially this is what we are doing. So we initialize everything to close to 0 values, and then we start off with every training sample. So for each training sample, I figure out the weight. I update the weight based on the gradient. And now let's look at, let's compare the perceptron and the gradient algorithm. Right? So the perceptron rule is guaranteed if they're linearly separable. We saw that. And if eta is small enough. What about the linear one? We use gradient descent, right? And then what happens is it's definitely guaranteed to converge somewhere. Why? Because of the parabolic thing. You're assuming a linear unit. A linear unit will have a parabolic shape. So it will definitely converge at some point. Right? And it will converge even when the training data contains some noise, because your surface still has a unique minimum somewhere. And even when the training data is not separable, still you will converge somewhere. So what is the practical issues here? One thing is, converging to a local minimum can be quite slow. Why? You have so many, xi's could be 10,000. And your error function sums it up over all the training samples. There was a summation over D there. So if you're doing that, it will be slow. And you have to repeat this iteration again and again and again and again. Right? So it can be fairly slow. And then there can be multiple local minima. I assume that it's a linear function, right? What if it, it's a linear thing, that the error function thing. I was not using a squashing function anymore. What if the whole thing is non-linear? Then you can have many, many local minima and you may get stuck there. We'll talk more about how we escape from those things later on. So one option then is, in the batch mode, the traditional mode that we have seen, this is what we are doing, right? We calculate the gradient and then we update. This ED, the gradient, you have to remember we sum it over all samples in our training data. And that's why it was slow. If I don't want to be slow, what I can do is I have a variation called the stochastic gradient descent. In stochastic gradient descent, I don't add all of them up. I don't work with all the samples at the same time. I pick any one of the training samples, maybe at random, that's fine. Or you can go sequentially, that's fine too. But you pick one training sample, any one training sample. And then, for that particular training sample, you figure out what the error is. And then, you compute the gradient, just based on one training sample. So this is quicker. I mean, it gets done quicker. But does it converge to the minimum at the same time? Maybe, maybe not. In general, maybe not. Right? But what we can say is, this stochastic thing can approximate the batch one, as long as you make error small enough. Now you're working on one input vector at a time. So, if you make a decision on one input vector, it is possible that you move very quickly from your actual minimum. But if you make eta small enough, you won't move too much. Just a little bit, just a little bit. So hopefully in the end, you will still end up at the same place if you were using gradient descent anyway, the normal version. So this was just a single neuron. But what we saw is, in general, we don't have a single neuron, we have multiple neurons. So how do we generalize whatever we have learned to multiple neurons? As an example, right? So this is an example of speech classification. And what these guys were trying to do is, they were looking at this. Let's say the first letter of a word is H, and then the last is D. Based on what is in between, we say it differently. So this is head. This is head. A little bit different, right? I am emphasizing. This is hod, had. So what people did is they recorded people saying these things. And the way they had and head is different is, I'm speaking different frequencies really. So we look at the frequency components. And then the figure out is, I can classify what you say based on looking at two different features based on those frequencies. But then the decision surface is not linear at all. It's a highly non-linear decision surface. So if you have a single perceptron or a single neuron, you cannot imagine that you will be able to classify this. So in order to solve problems like this, what you want is something like this. At least one layer of hidden neurons. How many of these will I need? We saw earlier, right? When I was going from 1, 2, 3, 4, 5, 6, I was able to classify more and more of my non-linearly separable variables. So now how many do I need? Sort of depends on how many of those lines I need to draw and so on. But you get the idea. And from there, how many outputs will I have? In this case, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So maybe I have 10 outputs, each corresponding to what kind of sound you make. Okay. And how many will I need here? It really depends on how these things are organized. So you can try one, maybe it doesn't work, you add, and figure out how many you need. Okay. So let's look at multiple layers. Right? So what kind of unit do I need for a multi-layer network? That's my first question. So previously we looked at a linear unit. What do I really need here? In this case, some things. If multiple layers are cascaded linear units, right? So this is a linear unit, this is a linear unit, this is a linear unit, then what will happen? What happens is, the output will only still produce linear functions. Straight lines. But if I want a line like this, a linear unit cannot produce it. A linear unit can produce a line like this, right? But it cannot produce this. So for example, here, if I want something like that with a curve, linear unit cannot do it. Right? So a linear unit was useful for us to understand and learn how to do gradient descent, but it's not really very useful in many practical cases. So what we do is, we need something else. And another thing is, we need a non-linear unit whose output is differentiable. Why? Because you have to calculate the gradient. So just because it's non-linear doesn't work, it has to be differentiable too. So let's see what our option is. The option is something we have seen before when we were talking neurons in the first place, in the case of the context of brains. And that was the sigmoid function. And we saw that the sigmoid, crap, I don't know why this is deleted, but we did calculate the derivative earlier, right? So the derivative of the sigmoid was, sigmoid and then 1 minus the sigmoid function itself. So that's fine. So now if I have a sigmoid function as my as the function defining my neuron, and now instead of having my linear unit, let's put a sigmoid unit at the end. And then I can go and do the same thing. I can find the gradient of the error function. The error function is still the same. The difference between what I want and what I am actually getting as the output. I take the square and half of that. Half is so that the 2's cancel out. Right? Previously when I did this, what did I get? I got t minus o times x. That's what I got. Now let's see what happens. If you do all of this math, what I will need is I need some kind of a chain rule and so on and so on. Maths is not important. But in the end, I will end up with something like this. I still have this term which says what is the difference between the input, in the target output and the real output that I'm getting. And then I still have this input xi. But in addition now I have this term, the output of the sigmoid unit, O times 1 minus O. But this is still nice, it's all a closed form thing, nothing very complicated to do. I still just need to look at the output and the input and the target value, and I can calculate the gradient. So it's not like I have to do some very fancy calculations, but I can still do it. Right? So now let's look at the algorithm then. What do I have to do? Now, I still have 2 minutes, give me 2-3 minutes more because I think we would want to finish at least the algorithm and then maybe look at some properties tomorrow. So this is what I have. I have some inputs. I have some hidden links. And I have some outputs. And then these guys are connected everywhere. I have 2 lines to the same thing, but anyway. Right. Let's just leave it at this. So when I give an input vector xi here, maybe I get an output here. Right? And let's make life easy. Let's say I just have only one output thing here. Only one output. What is the difference in that? So what can I observe? I can observe this and I can observe this. Right? So for this particular unit, I know what is the output. I know what is the target. So I can do some things easily. But for this particular unit, what was the output here? And what was the error? I know the error of this particular component, t minus 1. What was the error here? I don't know. So what I do is, the idea is this. I don't know what was the error of this, because I need to know the error to make this thing work, right? T minus O kind of thing. What was the error of this unit? I don't know. I know only the error at the output. So what I will do is I'll move it backwards. If this was the error, how much of this error was contributed to by this guy? I think that it was proportional to what was the weight here. So I will do that. And if there were many of those, I will take whatever errors I'm contributing to and I'll sum them up by applying the weights accordingly. Okay, that's the whole idea here. And then we can go through the whole thing. So for each output unit, I know what the error is, tk minus ok. So I can calculate the things. But for each hidden unit, now what I have to do is, I say this was the error at the output. And then I essentially multiply the error with the weight. And then say, okay, the total output was the total error at the output was something. My contribution was proportional to my weight. And then this is the same as I use to update my weights in my input side. So previously I looked at my output and I can figure out in the single neuron case, I look at my output and I can adjust my weights. I do the same thing, I look at the output, I can adjust my weights here, not a problem at the output layer. But for this now, I see what fraction of the output errors am I causing. That's my output error here. That I use to check my or update my weights on this side. Then for this guy also, I will do the same thing. What fraction of the errors was my responsibility? I will use that to control. Again, there are other things here. I will use that to control the weights on this side. That's the whole idea about back propagation, and this is just the implementation. Questions? Right. So I think it's a good time to stop. I didn't waste, well, I didn't take more than, it's exactly 11:30, so that's not too bad.
So there are some important announcements. Yeah, so the point is that one in the examination, this exam is the optional, not the compulsory. So if you want to give, you can give the examination on 22nd, 8:30 to 9:30. So there are two certificates, separate certificate. One is the participation certificate, that you all get the participation certificate on 9:30 to 10:30 on 22nd of December. That is the last day. And 8:30 to 9:30 is the examination. So if you are appearing in the examination, you will get the examination certificate either pass or fail and after 10 days or 15 days via post. Because we need to check the answer script and upload on the GIAN portal and other things. Different numbers of formalities are there. So we will check the answer script and doing that things, and result will be displayed on the website. Okay. Then we will display the certificate via post and other things. So certificate will take time. Examination certificate. So participation certificate you can get on 9:30 to 10:30 on 22nd of December. So yeah.
So the test, please make the timings a little later, because these are foggy conditions and I have to drive 40 to 50 kilometers. So please distribute certificates earlier and then test later. 8:30 to 9:30 certificate distributions, 9:30 to 10:30 test.
In that case, we already take the time by the dean and other things. Formality is already over for the examination, because this is the examination and it is little bit tough exam. Okay, not an easy task, because we need to display the results and question paper also and uploaded on these things. So examination timing changing is not possible. So 8:30 to 9:30 examination, certificate distribution is 9:30 to 10:30.
So this will be objective type or description?
That we will see. Right now we are not doing this.
It will be, I will not give you any problems to solve in general, right? So it's fairly easy. I just want to test you on some concepts. So some little bit of, even if I say description, don't write more than 2-3 lines. I want to see an essay there. Right? 2 lines, 3 lines at most. Maybe some true-false kind of questions. So it's simple enough.
So this exam is completely optional, not compulsory. So don't worry about if you are free, you want to give, you can give the examination. And other point is that those students they are outside from BHU or the IIT-BHU, if they want to discuss with the faculty or want to meet me or Dr. Tanima Datta, that we are available in our office between 1 PM to 3 PM. 1 to 3 there. So yesterday some students they approached us, but we are not available that time. So right now we are free. So second half, if you want, you can meet and discuss for any other next step or what will you want further. So you are free, you can meet in today's second half, 1 PM to 3 PM. Thank you.
Those who want to give exam, those who want to give exam, they should let us know by tomorrow morning. Tomorrow morning you have to let us know, because we have to give the details to the dean to our higher authority also. But okay, these are giving exams and we have to do the things. Okay. So those who have just think of it, those will give exams. So because it's a complete process, it's not like that we sit like this. It's a complete process that will follow in IIT. That process will be followed for your exam also. So let us know what it is.
किशोर बोयाट किशोर हाँ तो ये सारे हम लोग हैं ना
We will discuss at length.
XI is the ith sample value. Maybe it's a picture. So XI has 960. So when I say XI, input you're giving me. So this XI
इसमें कुछ नहीं है, एक्चुअली इलेक्ट्रिकल गेट को सर्च देखते देखते
XI1 will go here, XI2 will go here, at the input, right? So the number of, that's what you're asking for. You have a number of different values like temperature, humidity, and wind. So this is temperature, this is humidity, this is pressure. So these are all the waves of noise. In this case, so let's say temperature, humidity, pressure. So you have X1. This one has temperature 1. Humidity 1. Pressure 1. So this is X1. And this one has every time you do this, you use it, and maybe you have some layers. Maybe from here. You make it